Welcome to space science. Have astronomers finally found the strongest clues yet to the most mysterious world in our solar system, far beyond Neptune, in a region of darkness where sunlight barely reaches? Strange distant objects move in ways that do not seem random. Now, with the extraordinary infrared vision of James Webb, the search for Planet 9 is becoming sharper, deeper, and more fascinating than ever. If this kind of cosmic mystery interests, please like, subscribe, and share the video to support space science. Far beyond the bright inner lanes of the solar system, the scene grows wide, cold, and slow. The sun still rules this distance, but its rule becomes gentle rather than fierce. Light spreads thinly across an enormous volume of space. Warmth drains away. The familiar planets no longer fill the sky of thought. Instead, there is a frontier made of darkness, weak sunlight, scattered ice, and long emptiness between one object and the next. This is the outer solar system in its broadest sense, a region that begins beyond the known giant planets and continues outward into a vast gravitational domain that remains only partly mapped. Here the sun is no longer a blazing presence. It becomes a brilliant star surrounded by blackness, its light reduced to a pale wash compared with the strong daylight known near Earth. Any body moving through this distance reflects only a small portion of that weak light. A dark surface reflects even less. A cold atmosphere, if one exists, would hold little brightness. The outer frontier therefore hides objects very well, not because they are always small, but because distance itself dims them so severely. Even a world several times more massive than Earth can remain almost invisible when placed far enough from the sun. Astronomers often describe distance in the outer solar system with the astronomical unit, which is the average distance between Earth and the Sun. This unit becomes useful because ordinary kilometers grow unwieldy so quickly. Neptune, the outermost known giant planet, circles at about 30 astronomical units from the Sun. Beyond Neptune, the scale opens dramatically. Many distant bodies move on paths that carry them tens, hundreds, or even much farther in astronomical units. The difference between 30 and several hundred is not a simple extension of the same neighbourhood. It is a move into a much more diluted and difficult realm, where orbital periods stretch across centuries and into many thousands of years for the most remote objects. The outer frontier is not an empty shell. It contains structure, though that structure is sparse. There is the Kuiper Belt, a broad population of icy bodies beyond Neptune. There is the more disturbed and elongated population often called the scattered disk, where objects travel on stretched paths shaped by earlier gravitational encounters. Farther still lies the immense and more hypothetical Oort cloud, a distant reservoir of icy bodies thought to surround the solar system on truly enormous scales. Between these named regions, and within them, there are countless gaps, inclinations, crossings, and quiet trajectories that turn the solar system from a neat set of planet circles into a layered and dynamic system. The objects that occupy these outer reaches are built mainly from ices and rock. In this scientific context, ice means substances that freeze at low temperature, such as water, methane, ammonia, and other volatile materials. These substances can remain solid for immense spans of time in the weak sunlight beyond Neptune. The result is a population of ancient bodies that preserve conditions from the early solar system more clearly than the warmer worlds closer to the Sun. Their surfaces may be altered by radiation, impacts, and slow chemistry. Yet their broad existence still carries the memory of how the planets formed and moved. Motion in this region is patient. A body far from the Sun moves more slowly than one close to it because the Sun's pull weakens with distance. Its path remains bound, but the curve becomes vast and deliberate. Year after year, its position changes only slightly against the background stars. This slowness is one reason the outer solar system can conceal substantial objects. Survey images taken days apart may show almost no obvious motion. A distant world can resemble a faint, fixed star unless observations are repeated with exceptional care across much longer spans. The difficulty is not only seeing something faint, it is also proving that the faint point is a nearby member of the solar system, rather than a much more distant star or galaxy. Temperature adds another layer to the character of this frontier. Sunlight is so weak that many bodies here are extremely cold, often only a little warmer than the natural background of space. They do not shine by their own visible light. At most, they may release a small amount of stored internal heat, or absorb and re-radiate the little sunlight that reaches them. This means that the outer solar system is not best imagined as a bright collection of remote planets waiting to be photographed in ordinary light. It is better understood as a dim thermal landscape, where any hidden world may be easier to sense through faint infrared warmth than by reflected sunlight alone. This broad region also preserves the history of migration. The giant planets likely did not form exactly where they now orbit. Over long early ages, their gravitational interactions with surrounding material caused them to shift. Those shifts stirred, scattered, and rearranged outer populations of icy bodies. The distant frontier therefore acts like a historical record written in orbital paths. Its objects do not speak in words or colours, but in eccentricity, inclination, clustering, and attachment. Eccentricity is the measure of how stretched an orbit is. Inclination is the tilt of that orbit relative to the main planetary plane. These quiet geometric features contain evidence of long-past forces. Because the region is so large, a search within it is never a search through a single place. It is a search through an enormous volume where brightness, motion, and angle all work against easy detection. A world hidden there need not be tucked behind some physical barrier. It can remain unseen simply by being distant, cold, dark, slow, and placed against a crowded background of stars. The outer solar system is not merely far away. It is observationally unforgiving. It asks for repeated surveys, careful comparisons, and the willingness to treat absence of detection as incomplete knowledge rather than final proof. This is why the frontier beyond Neptune has become a region of scientific patience. It is large enough to host objects not yet catalogued. It is cold enough to keep them dim. It is dynamic enough to preserve signs of unseen influences. Observations indicate that the known solar system does not exhaust the full story of this distant domain. At the same time, it remains uncertain whether every unusual pattern found there requires a new planet. The broad outer frontier offers clues, but it does not yield them quickly. In this distant realm, the solar system is no longer a tidy family portrait. It becomes a fading field of light and ice held together by gravity across almost unimaginable distance. The sun remains at the centre, yet the edge feels less like an ending than a thinning out, where matter grows rare and time seems to slow. Here, in the wide dark beyond the giant planets, the search begins with space itself before it ever reaches any single object within it. Beyond the last large planet, the outer solar system does not open into pure emptiness. It enters a realm of small icy bodies spread across a broad and uneven band, a distant population that circles the sun in weak light and deep cold. This is the region commonly called the Kuiper Belt, though the name can suggest a neat ring when the true picture is more irregular and extended. It is not a solid wall of objects and not a tightly packed swarm. It is a sparse field of ancient remnants, each one separated from the next by enormous distances, yet together forming a meaningful outer population. In this far zone, the solar system begins to show its leftover material, the fragments that remain after planet formation and early rearrangement. These bodies are often called trans-Neptunian objects because they orbit beyond Neptune. Many are small, some are quite large, and a few are large enough to be counted among the dwarf planets. Pluto is the most familiar example, but it is only one member of a much wider population. Eris, Haumea, and Makemake belong to this distant company as well, each with its own surface, composition, and orbital path. Around them lie many smaller worlds, from substantial icy spheres down to irregular fragments whose shapes are governed more by their own material strength than by gravity. Together they create a region that is physically quiet but scientifically rich. The materials in this distant belt are important because they are ancient. These objects form from the same broad cloud of gas and dust that gives rise to the Sun and planets, but many of them do not become part of the larger worlds. They remain as preserved leftovers, altered by collisions, radiation, and slow chemical change, yet still carrying traces of early solar system conditions. Their ices may include water, methane, nitrogen, carbon monoxide, and ammonia, depending on size, temperature, and history. Their darker surface layers can be shaped by long exposure to sunlight and energetic particles, which change simple chemicals into more complex compounds over immense spans of time. This weathering can redden or darken a surface, making the body reflect even less light. The belt is not uniform. Some objects move on relatively moderate paths and remain in stable relation to Neptune. Others follow more stretched or tilted orbits. A stable relation of this kind is called a resonance, meaning that the orbital periods of two bodies fall into a regular pattern. Pluto, for example, is in resonance with Neptune in such a way that although their paths cross in projection, they never come close enough for collision. This resonance acts like a repeating rhythm in gravitational time. It does not require contact. It depends only on timing, geometry, and the steady pull of gravity over many orbits. In the outer solar system, such rhythms matter greatly because they shape where objects can persist. Farther out and farther from stability, some bodies belong to the scattered population. These are objects whose elongated or tilted paths suggest that Neptune or other early gravitational influences once shifted them outward. Their orbits can carry them from regions not too far beyond Neptune into much more remote reaches. Some pass inward enough to be disturbed again. Others remain on detached paths that keep them distant for almost all of their long years. These detached objects are especially interesting because they seem less connected to Neptune's present control. Their paths hint that something more than the known planets may have shaped them, or that the early solar system was more restless than it first appears. Even within this outer population, emptiness remains the dominant impression. If a traveller could move among these bodies, there would be no crowded belt of tumbling icebergs. There would be silence, darkness, and immense separation. One object would hang in the distance while countless others remained far beyond easy sight. The term belt is useful scientifically, but the lived image is closer to a cold archipelago scattered across a vast sea of blackness. Each member follows its own slow route around the sun, and most do so without any near encounter for ages beyond ordinary comprehension. Because these objects are small and far away, they are difficult to observe directly. Most appear only as faint points of light, too distant for surface detail, except in rare cases observed by powerful telescopes or visiting spacecraft. Astronomers learn about them first through brightness, colour, and orbital motion. brightness offers a rough combination of size and reflectivity, though the two cannot be separated easily without additional information. A larger dark body and a smaller bright one may appear similarly faint. Color gives hints about surface composition and exposure history. Motion, measured patiently against the background stars, reveals the orbit, and the orbit in turn places the object within the larger structure of the outer solar system. The importance of this distant debris lies not only in the bodies themselves, but in the pattern they collectively form. The Kuiper belt and the more stretched, scattered populations act as a record of gravitational shaping. Their present distribution is not random. It reflects the outcome of planet formation, migration, resonance trapping, scattering, and long-term orbital evolution. In that sense, the small icy bodies behave like dust left on the floor after the furniture of the solar system has been moved. The pieces are humble, but their arrangement remembers the motion of the larger forces. Some of the most distant known objects do not fit neatly into simple categories. Their orbits are so long and so detached that they spend most of their existence far from Neptune's direct influence. These are the bodies that attract special attention in the search for hidden gravitational structure. Their existence does not by itself prove that an unseen planet is present. Observations indicate only that the outer debris field contains members whose paths are unusual enough to demand careful explanation. It remains uncertain whether these paths arise from a distant planet, from subtle biases in where astronomers have looked, or from processes acting over the earliest ages of solar system history. Yet even without settling that question, the realm of icy debris has its own quiet significance. It shows that the solar system is not made only of the large, named planets. It also includes a vast outer memory of formation, where little worlds endure in the dim margin beyond Neptune. Their surfaces freeze, their motions slow, and their years lengthen into spans that outlast civilizations. They circle the sun with almost no drama, yet together they form the outer text from which astronomers begin to read deeper patterns. In this cold debris field, the search remains patient, grounded first in the many small bodies that can be seen before turning to the larger body that may still remain hidden. Among the many small bodies that move through the distant outer solar system, a few begin to stand apart not because they are bright or large, but because their orbits seem to lean in related ways. This is where the broad field of icy debris becomes something more exact. Astronomers stop looking only at where these bodies are and begin looking carefully at how they move. The key is not a photograph of a hidden world. It is a pattern inside orbital geometry, a subtle order that appears among a very small number of distant objects whose paths carry them far beyond the stronger present grip of Neptune. An orbit can be described by several properties. Its size tells how far the body travels from the Sun. Its shape tells whether the path is close to circular or strongly stretched. Its tilt shows how much the path rises above or dips below the main plane in which most planets move. There is also the orientation of the orbit, meaning the direction in space toward which its longest axis points. For ordinary experience, these details may seem abstract. In celestial mechanics, which is the study of motion under gravity, they are the language through which distant bodies reveal the forces that shape them. What makes the most distant objects interesting is not merely that their orbits are elongated. Many outer bodies have elongated paths. The unusual point is that several of the most remote known objects appear to have their long orbital axes grouped in a similar direction rather than scattered randomly around the Sun. Their closest approach points and their overall orbital alignments seem to cluster. In addition, some of these bodies share related tilts and detached paths. meaning that even at their nearest they remain too far from the Sun to be easily explained by ongoing close interaction with Neptune alone. The pattern is delicate and statistical rather than dramatic. No single orbit proves anything by itself. The significance comes from the repeated appearance of similar geometry in a small and unusual sample. To understand why this matters, it helps to imagine many distant bodies placed on long-stretched loops around the Sun, if nothing special organizes them. Then over long times their orientations might be expected to spread into many directions. Gravitational nudges pass scattering, and the slow precession of orbits would tend to mix the pattern. Precession is a gradual turning of an orbit's orientation over time, rather like the slow shift of a spinning top's axis, if. Despite this tendency towards spreading, several remote orbits remain grouped. Astronomers naturally ask whether some persistent influence is shepherding them into that arrangement. The known distant objects that motivate this discussion are extreme in their remoteness and in the shape of their paths. Their orbital periods can stretch across many hundreds or thousands of years. Their nearest points to the Sun remain far enough away that they do not seem to belong to the ordinary inner part of the scattered population, because they spend most of their time in the dark outer reaches. They are observed only near the limited portions of their paths where they become faintly detectable. This makes them difficult objects not only to discover, but also to interpret. The pattern seen among them therefore carries both value and caution. It offers a clue, but the clue is drawn from a sparse and biased sample. Observational bias is an important part of this story. A bias in this scientific sense does not mean error or carelessness. It means that the process of observation is not equally sensitive to all possible objects in all possible places. Telescopes do not survey the whole sky in the same way, at the same depth, in the same seasons, or against backgrounds of equal clarity. Some regions are searched more often than others. Some objects are easier to detect because of where they happen to be on their long paths when observations are made. Since distant bodies are usually found near the parts of their orbits where they are brightest, the sample available to astronomers is automatically incomplete. This means that an apparent pattern in orbital alignment may reflect a real physical structure, or it may be strengthened by the selective way discoveries happen. Even so, the observed clustering has remained compelling enough to sustain serious scientific attention. It is not based on a single body or a single measurement. It emerges from repeated study of a set of extreme trans-Neptunian objects whose orbital elements seem more organized than simple randomness would suggest. Some models indicate that a distant massive planet could maintain such a grouping over long periods through secular effects, which are slow gravitational influences that accumulate gradually over time rather than through repeated close encounters. Other analyses argue that the evidence weakens when discovery bias is modeled more fully, or when additional objects are included. Observations indicate a suggestive pattern. It remains uncertain how much of that pattern comes from nature, and how much from the way the search has unfolded. The geometry of these orbits also includes bodies on unusually tilted paths, and even some that move in directions difficult to produce with only the known giant planets acting under present conditions. Here again, the meaning is not simple. The outer solar system has experienced a long history, and that history may include migration, scattering, resonance, passing stars in the early stellar nursery, or collective effects from a much richer ancient debris field than exists today. Each of these possibilities can leave traces. The challenge is to decide which explanation best matches the full observed architecture of the distant objects rather than only one part of it. For this reason, the unusual orbit patterns are best treated as a structured hint rather than a solved message. They are real measurements of real bodies, Their alignments and detachment are not inventions, but the conclusion drawn from them must remain careful. A hidden planet is one possible organizing influence. It is not the only idea that has been examined. The strength of the Planet 9 case rests heavily on whether the clustering truly survives after all known biases are considered, and whether new discoveries continue to fit the same structure. In the cold silence beyond Neptune, the distant debris field begins to show something like grammar. The bodies do not simply drift at random. A few of their paths seem to share a quiet order, as though a gentle hand has been turning their long loops into related directions over immense time. Whether that hand belongs to an unseen planet or to some broader history written into the outer solar system remains unresolved. What is known is smaller and firmer. A rare group of remote objects displays orbital patterns unusual enough to demand explanation, and in those patterns the search first becomes precise. From these unusual distant orbits, astronomers begin to consider a larger cause. The small icy bodies themselves are not massive enough to organize one another. Their combined gravity in such a sparse region is too weak to maintain the persistent alignment that some studies describe. If a pattern is real and long-lived, then something more substantial must be shaping it. This is the point at which the Planet 9 hypothesis enters the outer solar system, not as a direct sighting, but as an attempt to explain order in motion. The hidden body is proposed first in mathematics and orbital behavior, long before it is seen in any image. The basic idea is calm and simple. If an unseen planet with several times Earth's mass moves on a very distant orbit, its gravity could slowly influence the paths of remote icy bodies over millions of years. It would not need to crash through the outer solar system like a dramatic intruder. It would not need to scatter every object in its path. A distant planet could act more gently than that. Through repeated long-term gravitational forcing, it could alter orbital orientations, stretch some paths, tilt others, and preserve a shared pattern among bodies that never come near it. In this view, the hidden planet becomes less like a bright missing object, and more like a steady sculptor of the dark outer frontier. Astronomers estimate the possible nature of such a planet by asking what kind of body could reproduce the observed structure. The answer in many studies is a world larger than Earth, but smaller than Neptune, perhaps a distant ice giant or super-Earth, moving on an orbit far beyond the known major planets. The proposed distance is immense. At its nearest, it may still remain hundreds of astronomical units from the Sun. At its most distant, it could travel much farther outward. Such an orbit would be elongated rather than nearly circular, and likely tilted relative to the main plane of the solar system. This matters because the geometry of the proposed orbit helps determine how its gravity would influence the remote trans-Neptunian objects over long spans of time. The mass estimate is also important. A body too small would not produce enough long-term effect. A body too large would disturb the known solar system more strongly than observations seem to allow. The suggested middle range gives the hypothesis its particular character. Planet 9, if it exists, is not imagined as another Jupiter hidden in plain sight. It is usually described as a more modest planet by giant planet standards, yet still large enough to dominate the architecture of the far outer system in ways no small icy body could match. Its power would come not from brilliance or heat, but from endurance. Over millions of orbits by the smaller bodies, its gravity would accumulate into structure. This slow accumulation is central to the idea, in celestial mechanics, a tiny pull repeated over very long times can produce major effects. The outer solar system provides exactly the kind of environment where this can happen. Distances are vast, orbital periods are long, and close encounters are rare. That means a distant planet does not need to strike an object directly to matter. It can change the average direction in which an orbit points. It can influence how stretched the orbit becomes. It can help produce detached paths that remain far from Neptune. These are called secular effects, meaning long-term changes produced by gravity acting gradually rather than suddenly. The Planet 9 hypothesis depends heavily on these slow processes. One of the most discussed possibilities is that the unseen planet could keep a group of extreme trans-Neptunian objects in a state of orbital anti-alignment. This means their long orbital axes would tend to point in a direction opposite to that of the planet's own orbit. The result is not a collision path, but a stable gravitational arrangement in which the smaller objects avoid disruptive encounters while preserving a shared orientation over long times. In computer models, this can create a pattern that resembles some of the clustering seen in observations. The language may sound abstract, yet the physical idea is steady and clear. A hidden planet can organize space not by being near, but by giving distant bodies a durable gravitational rhythm. The hypothesis also attempts to explain unusual orbital tilts. Some remote objects move on paths that rise steeply above the ordinary planetary plane. A sufficiently distant inclined planet might gradually excite such tilts, helping produce a population of bodies with surprising orientations. In this way, the proposed planet does more than explain one narrow feature. It offers a broader framework for why the outermost known objects may show both clustering and orbital oddity. A good scientific hypothesis often gains strength when it accounts for several observations at once rather than only one. Yet the idea remains a hypothesis because it begins from inference rather than detection. No telescope has yet delivered a universally accepted direct image of Planet 9. No confirmed track across the sky has been measured. No reflected spectrum or thermal signature has settled the matter. The argument is indirect. Astronomers observe distant bodies, measure their orbits, simulate many possible outer solar systems, and ask whether an unseen planet provides the best explanation. This method is legitimate and common in science, but it carries a natural limit. The result can be compelling without being final. There is also uncertainty within the hypothesis itself. Different studies suggest different masses, distances, tilts, and orbital shapes for the possible planet. These ranges matter because each version predicts slightly different sky locations and different strengths of influence on the outer population. The idea, therefore, does not point to a single precise body waiting at a single exact place. It defines a family of possible distant planets, whose shared feature is the ability to organize the remote debris field better than random distribution alone. As more objects are discovered and more biases are studied, the allowed possibilities can narrow or shift. In this stage of the search, the hidden planet exists as a gravitational proposal shaped by outer evidence. It is not yet a world with photographed clouds or measured seasons. It is a mathematical body whose presence is tested by whether the outer solar system behaves more naturally with it than without it. Observations indicate that some distant orbits may be unusually organized. The Planet 9 hypothesis asks whether a remote planet is the calm, persistent cause of that organization. It remains uncertain whether this is the correct explanation, but it provides a coherent way to connect many separate orbital clues into one invisible source. A distant planet does not need to be impossible to see in order to remain unseen. It needs only to sit in the narrow meeting place of weakness and distance, where light fades, motion slows, and the sky behind it becomes crowded with other faint points. This is the observational problem at the heart of the search. Once astronomers imagine a remote planet beyond the known giant planets, the next step is not simply to point a telescope outward and expect a clear image. The challenge is more exact than that. A distant world can hide in plain sight because the conditions of detection become severe long before the conditions of physical existence do. The first difficulty is reflected sunlight. Most planets in the solar system are seen, in the most ordinary sense, because they reflect the sun's light. Closer to the sun, this works well enough. Even dark bodies receive ample illumination, and their apparent motion against the stars is often measurable on human timescales. Far beyond Neptune, the situation changes. Sunlight weakens sharply with distance. A planet hundreds of astronomical units away receives only a tiny fraction of the light that falls on Earth. Then the return journey of that reflected light to a telescope on or near Earth weakens the signal again. By the time the light arrives, it may be so faint that only sensitive instruments and carefully chosen observing conditions can separate it from background noise. Surface reflectivity also matters. Reflectivity is the fraction of incoming light a surface sends back. A bright icy surface can help a distant body stand out. A dark surface can hide it much more effectively. Since the physical nature of a hypothetical Planet 9 remains unknown, astronomers cannot assume it is bright. If it has an atmosphere, its clouds might reflect light well, but if it has a dark outer layer or only limited reflective haze, then visible detection becomes harder. Two planets of similar size at the same distance could appear very different depending on how much light their outer layers return. Distance affects more than brightness. It also reduces apparent motion. A faraway planet moves slowly in its orbit because the sun's pull is weaker there. From Earth, that slow orbital motion is combined with parallax, which is the apparent shift in position caused by Earth moving around the Sun. Parallax helps reveal that an object belongs to the solar system rather than to the distant stellar background. But for a very remote planet, the change can still be small and gradual. A faint object that shifts only slightly from night to night can be hard to distinguish from a fixed source, especially if survey images are not designed for that exact timescale. The object may need weeks, months, or even longer comparison intervals to show a convincing track. The background sky introduces another problem. A telescope searching for a faint distant planet does not look into a clean black void. It looks through fields crowded with stars, galaxies, detector artifacts, cosmic ray hits, and subtle noise patterns. In visible surveys, a remote planet may appear as one more dim point among countless others. In infrared observations, where a cold planet might be easier to notice, the sky still contains many sources of confusion. A search therefore becomes an exercise in elimination. Astronomers must ask not only whether a faint source exists, but whether it moves, whether it has the expected brightness, whether it repeats in later observations, and whether it can be excluded as a known background object or instrumental effect. Sky area is a further limit. Even if models suggest a likely range of distances, masses, and orbits, the possible search region can still span a large part of the sky. A telescope with a small field of view may be very sensitive, yet still inefficient if the hidden target could be located across many square degrees. This creates a trade between depth and breadth. Wide surveys cover large regions but may not reach the faintest limits. Deep observations can detect dimmer objects but only in narrower fields. A distant planet can therefore escape detection, not because no telescope is powerful enough in principle, but because the available observing time, field coverage, and sensitivity must all be balanced carefully. Timing matters as well. The position of a hypothetical outer planet changes very slowly, but the conditions for observing it from Earth do not remain constant. Some sky regions are easier to observe in certain seasons. Some lie near the plane of the Milky Way, where the background becomes especially crowded. Atmospheric conditions affect ground-based searches. Moonlight can reduce sensitivity. Even archived survey data may leave important gaps between fields or between times of observation. A hidden planet needs only to occupy one of these difficult regions at the wrong brightness and the wrong motion scale to remain undetected. Heat offers a second path to detection, but it also carries limits. A planet does not only reflect sunlight, it can emit faint thermal radiation, meaning weak heat glow, especially in infrared wavelengths. This can help because thermal emission depends not only on reflected sunlight, but also on the body's own temperature and possible internal heat. Yet a remote planet would still be cold, and its thermal signal could be extremely faint. Instruments sensitive to infrared light can improve the situation, but the signal remains small and the planet's exact temperature is uncertain. A larger or younger planet might glow more strongly. An older or smaller one might fade into the threshold of detectability. The search is further complicated by model uncertainty. Astronomers do not know the exact mass, orbit, surface, atmosphere, or temperature of Planet 9, if it exists. Every unknown changes the expected brightness. A more distant planet on a highly elongated orbit may spend most of its time in a region where it is much dimmer than early estimates suggest. A lower mass planet may reflect or emit less light than a larger one. Even the tilt of the orbit affects where observers should look. This means a non-detection does not immediately destroy the hypothesis. It may only remove one part of the possible parameter space, which is the allowed set of physical and orbital properties. For this reason, the limits of direct detection are not a single wall, but a layered difficulty. Weak sunlight, uncertain reflectivity, faint thermal emission, slow motion, crowded background fields, incomplete sky coverage, and uncertain orbital predictions all combine. Each factor alone might be manageable. Together they create a wide hiding place. The hidden planet, if real, need not be especially clever. The geometry and physics of the outer solar system are enough to conceal it. So the search remains patient and technical rather than dramatic. Observers refine likely regions, compare old and new images, measure tiny shifts, and slowly exclude what can be excluded. The absence of a confirmed direct image does not mean the search has failed. It means the outer solar system continues to impose its natural conditions. In that weak light and slow motion, a distant world can remain physically present while staying observationally elusive. Suspended between theoretical expectation and visual proof, when astronomers search for a distant cold world, ordinary visible light is only part of the story. Far from the sun, a planet reflects so little sunlight that the search must often turn toward another form of seeing. This is the realm of infrared observation, where telescopes are built to sense longer wavelengths of light associated with heat. In this outer darkness, heat does not mean warmth in the human sense. It means a faint thermal glow. The quiet release of energy from a body that's cold by everyday standards but still not at absolute zero. For a hidden planet in the far solar system, this difference matters. A world that is too dim in reflected light may still leave a detectable trace in infrared light if instruments are sensitive enough. Infrared astronomy begins with a simple physical truth. Every object above absolute zero emits radiation. The hotter the object, the shorter and stronger the wavelengths it tends to emit. Very hot stars shine strongly in visible and shorter wavelengths. Much colder bodies, such as distant planets, moons, dust, and faint outer debris, emit most of their energy at longer wavelengths. In practice, this means that a cold remote planet may be better searched for through its thermal emission than through the small amount of sunlight it reflects. The signal remains weak, but it belongs more naturally to the object itself rather than depending entirely on the sun's fading illumination. This advantage has limits, but it is real. Reflected light falls sharply as distance from the sun increases, because the distant object receives less sunlight and then sends back only a fraction of that already weakened light. Thermal emission also depends on distance when observed from Earth, but it is not reduced by the same two-step loss of sunlight out and reflected light back. If a remote planet retains internal heat from its formation, or if its atmosphere traps some energy, then its infrared glow may remain more favorable than its visible brightness. Even so, the planet would still be faint. Infrared astronomy does not make the outer solar system bright. It only changes the balance of what may be easiest to detect. To make use of this, telescopes must be designed for the infrared with great care. Heat from the telescope itself can overwhelm the signal from cold cosmic targets. A warm mirror, warm instruments, or sunlight falling onto the spacecraft can create exactly the kind of background that hides the faint object being sought. For this reason, infrared space telescopes are placed far above Earth's atmosphere, which itself glows and absorbs strongly in parts of the infrared. They are also cooled, shielded and engineered to suppress their own thermal noise. Noise in this context means unwanted signal, not sound. It is the false background against which a real faint source must be distinguished. Space is therefore the natural home for the most sensitive infrared eyes. On the ground, even powerful telescopes face atmospheric turbulence, thermal emission from the air, and absorption by water vapor and other molecules. In orbit or deep space, these barriers are greatly reduced. A telescope can stare longer, detect fainter sources, and measure more precisely how much light arrives at different wavelengths. This makes space-based infrared astronomy especially valuable for studying coal dust, faint galaxies, exoplanet atmospheres, distant moons, and potentially hidden outer solar system bodies. Different infrared telescopes serve different roles. Some survey large areas of sky at modest resolution, building broad maps that can reveal moving or unusually coloured sources. Others observe smaller fields with much greater sensitivity, examining selected targets in extraordinary detail. Wide surveys are useful because the sky region where a hidden planet might lie can be large. Deep-pointed observations are useful because a cold planet may be very faint. The search for Planet 9, if it is to succeed, depends on both approaches working together. Broad search programs narrow the possibilities. More sensitive instruments then test the remaining regions with greater care. Infrared detectors also allow astronomers to compare wavelengths in ways that visible searches alone cannot. A distant star, a background galaxy, a brown dwarf, a dust cloud, and a cold solar system planet may all appear as dim points in an image, yet their energy is distributed differently across wavelengths. By measuring brightness in multiple infrared bands, astronomers can begin to classify what kind of source they are seeing. This does not always identify an object immediately, but it helps separate likely moving solar system bodies from the far richer background of distant astrophysical sources. In this way, infrared observation is not just about seeing faintly, it is also about sorting carefully. For a possible Planet 9, the most useful expectation is modest. Infrared telescopes are not guaranteed to reveal a bright, isolated planet glowing clearly in black space. More often, they help constrain possibilities. They can rule out some combinations of size, distance, and temperature. They can test whether a faint source has colours consistent with a cold planetary body. They can compare repeated observations to see whether something shifts position slowly over time. In some cases, they can detect objects too faint for ordinary visible surveys. In other cases, they simply show that if a hidden planet exists, it must be colder, smaller, darker, farther away, or placed elsewhere than earlier guesses allowed. This method has already shaped outer solar system searches in broader ways. Earlier infrared missions helped exclude parts of the parameter space for unseen large bodies by showing that no bright, warm giant planet appears in certain regions or above certain brightness levels. That does not settle the Planet 9 question, because the proposed object is generally thought to be much fainter and more distant than those excluded cases. Still, it illustrates how infrared astronomy works in practice. It often progresses by narrowing absence into information. What infrared eyes in space provide, above all, is a change in perspective. The outer solar system stops being only a region of weak reflected sunlight and becomes a region where temperature, internal energy, and long wavelength emission also matter. The cold dark is no longer featureless. It contains gradients of faint heat that carefully built instruments can measure. A possible distant planet remains elusive, but it no longer belongs wholly to invisibility. It enters a domain where hidden worlds may reveal themselves by the small energy they continue to release. So the search grows quieter and more refined. Instead of looking only for brightness in the ordinary sense, astronomers begin to look for warmth without warmth, motion without speed, and presence without easy contrast. Infrared space telescopes are made for exactly this kind of work. They do not solve the mystery by themselves, but they extend human sight into the temperature of darkness, where a distant planet may be dimly present even when sunlight is no longer enough. In the search for a distant cold planet, the James Webb Space Telescope enters not as a wide sky surveyor, but as an instrument of unusual sensitivity. It is built to detect faint infrared light with exceptional precision, and that gives it a special place in any careful discussion of hidden outer worlds. Webb does not scan the whole sky quickly in the manner of a broad mapping mission. Its strength lies elsewhere. It studies selected regions and chosen targets with deep attention, gathering light that is too faint for many other instruments to examine clearly. In the outer solar system, where objects are cold, dim, and slow, that strength becomes highly relevant. Webb is an infrared space telescope with a large primary mirror and instruments designed to work at wavelengths longer than visible light. Its mirror collects much more light than smaller infrared observatories can gather, and its location in space keeps it above Earth's atmosphere, where infrared observations would otherwise be blurred and partially blocked. The telescope also carries a large sunshield that protects it from sunlight and helps keep its instruments cold. This cooling is essential. A warm telescope would produce too much of its own infrared glow, making the faint signal from distant cold objects much harder to detect. Webb therefore works not only through size and optical quality, but through careful thermal design. This makes Webb especially powerful for studying faint sources in deep space and subtle thermal signals closer to home. In the context of Planet 9, its role is often described with caution because the telescope was not designed specifically to conduct a full-sky hunt for a hidden planet. Its field of view is limited compared with the huge possible search region, if astronomers do not know where to look. Even a very sensitive telescope can spend its time efficiently only on small selected parts of the sky. For that reason, Webb is most useful after other evidence narrows the likely region. It is a tool for refined searching and close examination rather than for first covering the entire outer darkness. Still, once a candidate region becomes plausible, Webb offers major advantages. A distant planet that is too faint for ordinary visible observation may still produce measurable infrared light. If that body retains some internal heat, or if its atmosphere and size place it within Webb's sensitivity under the right circumstances, the telescope could help detect or constrain it, even when no direct detection occurs. Webb can place valuable limits on how bright, warm, or large such a planet could be in the observed region. In science, this kind of negative result is not empty. It trims the range of possibilities and sharpens the search. Webb's sensitivity also matters because of the nature of the proposed planet itself. Planet 9, if it exists, is usually imagined not as a blazing object but as a cold, distant world, perhaps several times the mass of Earth. Such a body might resemble a small ice giant, perhaps with a thick atmosphere and some leftover heat from formation. At great distance, its reflected sunlight could be extremely weak. Infrared light may offer a more promising path, especially in the longer wavelengths where cold bodies emit more naturally. Webb's instruments are designed to measure faint infrared sources with precision, making it one of the few observatories capable of probing such low levels of emission in selected locations. There is also the matter of angular resolution, which is the ability to distinguish one point of light from another nearby point. In crowded backgrounds, this becomes important. A distant planet may lie against a field of stars and galaxies. If the telescope cannot separate faint neighbouring sources clearly, confusion increases. Webb combines sensitivity with sharp imaging, helping astronomers distinguish compact objects and compare repeated observations carefully. This does not make the problem easy, but it improves the ability to tell whether a faint signal behaves like a distant background source or a possible solar system body. Repeated observation is central here. A hidden planet should move slowly against the distant background. Webb can return to the same field and look for that subtle shift. Because the expected motion is small, precision matters greatly. A single image may reveal a faint point. Two or more well-spaced images may reveal whether the point belongs to the solar system at all. This is one reason Webb's role can be scientifically powerful, even with a narrow field of view. It can test candidate sources patiently, comparing position and brightness over time with high accuracy. Webb can also help in another way. It can study known distant solar system objects whose physical properties overlap with what might be expected for Planet 9 on a smaller scale. By observing remote icy bodies, dwarf planets, and other cold outer members of the solar system, astronomers improve their understanding of surface reflectivity, thermal behavior, atmospheric possibility, and infrared appearance. These observations do not reveal Planet 9 directly, but they build a more realistic framework for how a distant cold world might look to an instrument like Webb. In that sense, the telescope helps define the target even before the target is found. Yet care is necessary. Webb has not provided a confirmed discovery of Planet 9. Public discussion sometimes moves faster than the underlying evidence, especially when a powerful telescope is involved and a famous mystery remains unsolved. Observations may reveal candidate sources, interesting constraints, or data that refine where astronomers should look next. None of that is the same as a verified new planet. The proper scientific position remains measured. Webb expands the reach of observation into very faint infrared territory. It strengthens the search. It does not remove uncertainty by itself. What Webb changes most is the depth of attention available in the outer solar system. It extends human sight into weak thermal light with unusual clarity. It can examine narrow parts of the sky where a hidden world may plausibly lie, and ask whether anything faint, cold, and slowly moving is present there. If nothing appears, the silence itself becomes informative. If a candidate appears, the case becomes sharper and more testable. In either outcome, Webb turns a vague outer darkness into a more disciplined observational space. So within the larger Planet 9 search, Webb occupies a specific and valuable place. It is not the telescope that first surveys everything. It is the telescope that looks more deeply once the search has been narrowed. It brings sensitivity, sharpness, thermal control, and infrared reach to one of the faintest planetary questions in astronomy. In the cold margin beyond the known planets, that is a significant form of sight. It is not yet discovery, but it is a clear extension of where evidence can go. The deep sky is full of light that does not belong to the solar system. Behind any possible distant planet lie stars of the Milky Way, far galaxies, diffuse glow, detector noise, and small irregular marks created by instruments and energetic particles. To search for a hidden world in such a field is not simply to look outward. It is to sort one faint point from countless others, and to decide whether that point is truly nearby in astronomical terms, or only appears in the same line of sight. This is where repeated observation becomes essential. A distant planet may be dim, but it should move. The background, however crowded, is mostly fixed on the timescale of solar system searching. The work of the search is therefore the work of separating slow motion from apparent stillness. A single image rarely settles anything. It may show a faint source, but that source could be almost anything. It could be a distant galaxy, a background star, a known object already catalogued, a cosmic ray strike on the detector, or a subtle artifact of image processing. For a hidden planet, the crucial signature is not simply presence, but change of position over time. Because such a planet would move slowly, the change may be very small. Astronomers must return to the same patch of sky, often with careful spacing in time, and compare the new image with the old one at high precision. The goal is to find a point that shifts in a manner consistent with the distant solar system body, rather than remaining fixed like the much more remote background. This process begins with image alignment. Observations made at different times must be placed on the same geometrical frame so that stars and galaxies fall into matching positions. Even tiny differences in pointing, rotation, or detector geometry can complicate the comparison. Once the frames are aligned, astronomers can subtract one image from another. Subtraction in this context means removing the light pattern common to both images so that stationary sources fade away and changes become easier to see. If done well, the fixed background nearly disappears, leaving residual signals where something has moved, brightened, dimmed, or varied in another way. A slowly moving planet could appear in such a subtraction as a pair of faint residual marks, one where it was and one where it is. The exact pattern depends on the time spacing, the observing method, and the brightness of the source. Sometimes the result is not so clean. Real detectors have imperfections. The sky background is not perfectly smooth. Faint galaxies may have shapes that leave troublesome residuals. Variable stars can confuse the field. Cosmic rays can create false points in one exposure but not another. Because of this, subtraction is only the start of interpretation, not the end. A promising residual must be checked across multiple exposures and multiple filters if possible, then compared with known catalogues and expected motion models. This careful removal of the static background is especially important for a telescope like James Webb. Webb can detect very faint infrared sources with high sensitivity, which is great strength, but the same sensitivity means it also records a rich and complicated background. Deep images can contain extraordinary numbers of distant galaxies, many of them unresolved to the eye and appearing only as tiny dim points. A candidate hidden planet may therefore sit in a field where the difficulty is not seeing something faint, but deciding what kind of faint thing it is. Repeated observations allow astronomers to use motion as a filter more powerful than brightness alone. Time spacing matters greatly. If observations are too close together, a distant planet may not have moved enough to stand out. If they are too far apart, the expected position may become more uncertain, and field conditions may change. The correct spacing depends on the estimated distance and likely apparent motion of the target. Astronomers model how a distant body should shift because of both its own orbital motion and parallax. The apparent displacement caused by the changing position of the observer. For Webb, which orbits near the Sun-Earth second Lagrange point rather than sitting directly on Earth, this geometry is slightly different from that of a ground-based telescope, but the principle remains the same. A true solar system object reveals itself through a measured and physically consistent shift against the fixed background. Background subtraction also interacts with color. A distant planet may have an infrared brightness pattern different from that of stars or galaxies. If a candidate source appears in one wavelength band but behaves oddly in another, that can help classify it. Yet color alone is seldom enough, because some background galaxies can mimic faint planetary colors, and some instrumental effects vary with wavelength. Motion remains the most reliable guide. The sky may contain many faint red sources. It contains far fewer faint red sources that drift exactly as a distant outer solar system body should. This method of sorting motion from stillness requires patience and restraint. A single unusual dot is not a discovery. A source seen in only one epoch is not a new planet. Even a source that moves slightly must be tested against known minor planets, detector features, and statistical chance. The process resembles careful reading more than sudden revelation. Each new exposure becomes another sentence in a very sparse text. The astronomers ask whether the same faint point returns where orbital mechanics say it should return. They ask whether the background has been removed cleanly. They ask whether the signal survives different reductions of the data. Only when the candidate remains consistent under these tests does it begin to deserve deeper attention. In this way, the deep background becomes not merely an obstacle but a structured reference frame. The still stars and distant galaxies provide the fixed grid against which motion can be measured. Their abundance complicates the image, yet it also makes precise comparison possible. A hidden planet does not emerge by overpowering the sky. It emerges by drifting through it in a disciplined way, leaving a tiny trail of positional evidence across repeated observations. So the search in deep infrared images is a quiet act of subtraction and return. Astronomers align, remove, compare, and repeat. They let the stationary universe fall away as much as possible and watch for the faint source that refuses to remain in place. If Planet 9 exists, and if it lies within a field that Webb or another telescope examines deeply enough, this is how it is most likely to separate itself from the immense background, not as a sudden bright world, but as a slow, moving point, patient enough to be seen only by those willing to look twice and then again. A distant planet hidden in the far outer solar system would not announce itself with bright reflected light alone. At such great distance, sunlight becomes weak, and whatever light the planet sends back into space becomes weaker still by the time it reaches a telescope. For this reason, astronomers also think in terms of thermal light, the faint infrared emission that comes from the body's own temperature. This does not mean a hot glowing planet. It means a world that remains slightly warmer than the background of space and slowly releases energy at wavelengths invisible to human eyes. In the search for Planet 9, This soft thermal signal becomes one of the most important clues that a hidden world might leave behind. Thermal light depends on several physical properties at once. Size matters because a larger body has more surface area from which radiation can emerge. Temperature matters because warmer bodies emit more strongly and at somewhat shorter infrared wavelengths than colder ones. Distance matters because even a real signal spreads and fades as it travels outward to the observer. Internal heat matters too. A planet does not only respond to sunlight falling on it, it can also retain heat left over from its formation and release that energy slowly across immense spans of time. If Planet 9 exists and resembles a small ice giant or a super-Earth with a thick atmosphere, then some part of its detectability may depend on how much internal warmth it still carries in the present age of the solar system. This makes thermal light different from reflected light in a useful way. Reflected brightness depends strongly on how much sunlight reaches the planet, and on how much of that light the surface or atmosphere sends back. A dark world can hide very effectively invisible light. Thermal emission is not free from uncertainty, but it depends less on surface brightness and more on the planet's physical state. A larger, darker planet might still be easier to sense thermally than optically. A smaller, brighter one might show the opposite balance. That is why astronomers often model both channels together. They ask not only how much sunlight a planet reflects, but how much heat it emits, and which of those two signals is more favourable at a given distance. The difficulty is that temperature itself is uncertain. A distant planet far beyond Neptune would receive very little solar energy. Left to sunlight alone, it would be extremely cold. But planets are not perfect passive stones. A substantial body can trap internal heat within its deep layers and atmosphere. Uranus and Neptune offer reminders that outer planets are not defined by sunlight alone. Their thermal behaviour depends partly on what happens inside them. Not only on what reaches them from the Sun. A hypothetical Planet 9, though likely smaller than the known ice giants, might still possess enough retained heat to emit a faint but meaningful infrared signal. Observations and models can estimate such possibilities, but they cannot fix them precisely until the object is found. A planet's atmosphere would complicate the picture further. If a distant world has a thick envelope of gas, that atmosphere could affect how heat escapes. Some wavelengths might emerge more easily than others depending on composition, clouds, and temperature structure. Methane, hydrogen, helium, and more complex compounds could all shape the spectrum, which is the distribution of emitted light across wavelengths. In principle, a measured spectrum could reveal much about the planet's nature. In practice, that comes much later. At the search stage, astronomers are often dealing with far less. They may have only a faint brightness in one or a few infrared bands, not a full detailed fingerprint. Even so, the amount and colour of that thermal light can begin to constrain size, distance, and temperature together. These constraints are never perfectly separate. A somewhat larger, colder planet can produce a similar observed signal to a somewhat smaller, warmer one. A more distant, warmer planet can resemble a nearer, colder one. This is one of the central limitations of thermal interpretation. The light can indicate what combinations are plausible, but not always which one is correct. Astronomers therefore combine thermal estimates with orbital expectations from the Planet 9 hypothesis. If a certain sky position, apparent motion, and brightness all fit a narrow range of possible masses and distances, then the case for a candidate becomes stronger. If the signal fits too many unrelated possibilities, then the source remains ambiguous. This is why thermal light is best understood as a clue rather than a complete answer. It can say that an object is cold rather than hot, nearby in the solar system rather than far beyond the galaxy if it moves appropriately, and large enough or warm enough to match planetary expectations. But it may not immediately say whether the object is the long-sought Planet 9, a different minor body, a brown dwarf, or some other source until repeated imaging and orbital confirmation are added. Brown dwarfs, which are bodies larger than planets but too small to sustain the long-term hydrogen fusion of stars, can also emit infrared light and may appear faintly in similar searches. Motion and location help separate these possibilities, but the ambiguity must be respected. Webb and other infrared-capable observatories matter here because they can push the threshold lower. They can detect fainter thermal sources and measure them with better precision than many earlier instruments. That means the allowed hiding places for a distant planet can be reduced. If a region of sky is searched deeply and no suitable thermal source appears, then some models of Planet 9 become less plausible in that region. Perhaps the planet would have to be colder than expected, smaller than expected, farther away, or absent from that patch of sky altogether. In astronomy, such narrowing is progress. The mystery becomes tighter even when the object itself is not yet secured. At the same time, thermal searches must remain modest in what they claim. A faint infrared source alone does not reveal a whole world in detail. It does not immediately yield a cloud map, a composition table, or a direct planetary portrait. It gives a small measured excess of light, often at the edge of sensitivity, and asks for cautious interpretation. The most responsible scientific language therefore remains conditional. Observations may indicate a candidate source. The measured brightness may be consistent with a cold distant body. It remains uncertain whether the source is planetary until its motion, persistence, and orbital behavior are confirmed. In the quiet physics of the outer solar system, thermal light becomes a whisper from matter itself. It is the planet's own faint release of energy, separate from the weak sunlight that reaches it. For a hidden world, that whisper may be more revealing than reflected light, yet it still speaks softly enough that many meanings can overlap. Astronomers listen to it carefully. From that small warmth in darkness, they try to infer size, temperature, and distance without demanding more certainty than the data can truly provide. The clue is real, but it remains partial, and in that partial light the search continues. As new observations accumulate, the search for Planet 9 does not usually leap forward by finding the planet itself. It advances by making some parts of the sky less likely and others more worthy of attention. This narrowing is one of the quiet disciplines of astronomy. A hidden object far beyond Neptune may remain unseen, yet every careful survey still changes the shape of the problem. Areas that have been searched deeply enough can begin to fall away from the map of plausible hiding places. Models can be updated, orbits can be refined. What remains is not certainty, but a smaller and better defined region of possibility. This process begins with the predicted orbit. The Planet 9 hypothesis does not place the planet at a single fixed point in the sky. It suggests a family of possible paths based on how a distant massive body might organize the unusual orbits of extreme trans-Neptunian objects. Each possible path corresponds to a range of sky positions, distances, brightnesses, and apparent motions. The more uncertain the orbit, the broader the search zone. As astronomers improve the dynamical models and add new outer solar system objects to the analysis, some of those paths become less consistent with the full observed pattern, while others remain viable. In this way, theory itself trims the sky before the telescope even begins to look. Observation then applies a second cut. When a region has been surveyed to a certain depth and no suitable candidate is found, that non-detection matters. It does not prove that Planet 9 is absent from the entire sky. It only means that in that particular region, under the assumptions of that search, some possible versions of the planet become less likely. If the search is sensitive enough to detect an object above a certain brightness and motion threshold, then any unseen planet in that field may have to be fainter, slower, farther away, darker, smaller, or simply not there. One deep search therefore removes part of the allowed space. Many such searches, combined carefully, begin to carve the larger uncertainty into a smaller shape. Brightness limits are especially important in this narrowing. Every survey has a threshold beyond which sources become too faint to detect reliably. If models suggest that Planet 9 should be brighter than that threshold in a given field, and yet no object appears, then that version of the model weakens. If, however, the planet could still be below the threshold because it is colder or more distant than expected, then the region cannot be fully excluded. This is why narrowing the search is gradual rather than absolute. The sky is not divided simply into found and not found. It is divided into better tested and less tested parts, each with different sensitivity to different kinds of hidden planets. Motion limits matter as much as brightness. A distant planet moves only slightly across the sky, and surveys are not equally good at catching every rate of motion. Some are designed for relatively rapid minor planets. Others are better at very slow parallax shifts spread across days or months. If the hidden planet moves more slowly than the survey can confidently recognize, it may slip through the search even if it is bright enough. A well-designed targeted search therefore narrows the zone not only by looking deeply, but by matching the expected motion scale of a very distant world. Regions observed with the wrong timing may remain less constrained than regions studied with more appropriate cadence. The background sky also shapes the narrowing. Some parts of the sky are crowded by the Milky Way, where the density of stars and the complexity of the field make faint source searches much more difficult. A hidden planet passing through such a region may remain harder to isolate than one in a cleaner background. For that reason, some areas that have technically been observed are not equally well excluded. The search map is uneven. Clear high latitude fields may be constrained more strongly than crowded stellar regions. As a result, the plausible hiding places for Planet 9 do not shrink into a tidy circle. They become an irregular geography shaped by observational depth, background confusion, and the evolving predictions of orbital models. Infrared observations add another layer to this refinement. If a region is searched with sensitive infrared instruments and no suitable thermal sources found, then warmer or larger versions of Planet 9 in that region become less likely. Visible light surveys constrain reflected brightness. Infrared observations constrain faint heat emission. Together they can close off more of the parameter space than either method alone. Still, the narrowing remains conditional. A planet with lower internal heat, a darker atmosphere, or a different distance along its orbit may continue to evade detection in places where brighter or warmer versions would already have been found. New distant minor planets also reshape the likely zones. Every newly measured extreme trans-Neptunian object either strengthens or weakens parts of the original clustering argument. If new objects continue to show related orbital structure, the dynamical picture may favor certain planetary configurations more strongly. If the pattern becomes less coherent, the preferred search regions may spread or shift. This means that the map of plausible sky zones is never determined by telescope imaging alone. It also depends on the changing orbital census of the outer solar system. Each new small body contributes a quiet vote to the larger gravitational picture. James Webb enters this stage not by sweeping the whole sky, but by helping test selected fields more deeply once theory and prior surveys have reduced the options. A refined candidate region can be examined for faint thermal sources and slow motion with greater sensitivity. If nothing appears, the zone becomes harder to defend for planets within Webb's reach. If a source appears and survives repeated checks, the search sharpens further. In this way, Webb does not create the narrowed map by itself. It helps interrogate the remaining islands of plausibility after broader methods have already done much of the first reduction. So the search zones contract slowly, not dramatically. Whole regions are not erased in a single gesture. They fade in confidence as better data arrive. Some remain open because they are observationally difficult. Some remain open because the models still allow dimmer and more distant planets there. Others become less attractive because repeated searches have found nothing that fits. Observations indicate that the likely hiding places for Planet 9, if it exists, are not limitless. It remains uncertain exactly where the surviving regions lie in any final sense, because those regions depend on assumptions about mass, orbit, temperature, and discovery bias. Yet the broad picture is clear. The outer mystery is being pressed inward, one excluded patch of sky at a time, until what remains is not the whole dark frontier, but a smaller set of shadows still worth searching. Once astronomers propose that a hidden planet may be shaping the far outer solar system, they must test that idea in motion rather than in words. This is where simulations become essential. A simulation in this context is a numerical model that follows how bodies move under gravity across long spans of time. Instead of watching the real solar system for millions or billions of years, astronomers let equations carry virtual planets and small icy bodies forward step by step. They begin with assumed masses, orbital shapes, tilts, and starting distributions, then ask whether the resulting system develops the same patterns that telescopes actually observe. In the case of Planet 9, this method has become one of the central ways to judge whether a distant, unseen world makes the outer solar system more intelligible. These simulations are not simple drawings of ellipses. They are dynamic calculations in which gravity is allowed to work continuously. The known giant planets are included. In many modern studies, the smaller trans-Neptunian objects are placed on a wide variety of trial orbits. The proposed Planet 9 is then added with a chosen mass and orbit, and the model is evolved over very long times. Some simulations also include wider influences such as the galactic tide, which is the very weak gravitational effect of the Milky Way on distant solar system bodies and passing stars, which can gently disturb far outer orbits over immense timescales. The goal is not to reproduce every single object exactly. It is to see whether the overall architecture that emerges resembles the real distant solar system better with Planet 9 than without it. The main test is whether a simulated Planet 9 can generate the kinds of unusual orbital patterns that astronomers have measured. These include the apparent clustering of some extreme trans-Neptunian objects, the presence of detached orbits that remain far from Neptune, and certain high inclination or otherwise unusual paths. If the simulated system naturally creates these features and keeps them stable for long periods, that counts as support for the hypothesis. If the same patterns appear just as easily without the extra planet, then the case weakens. In this way, the simulations act like a filter for ideas. They do not tell astronomers whether Planet 9 exists with certainty, but they show whether the hypothesis behaves plausibly under the known laws of motion. One reason these models matter so much is that the outer solar system evolves slowly. The gravitational effects proposed for Planet 9 are mostly secular, meaning they build up gradually over long times rather than through one dramatic close encounter. a distant planet may preserve orbital anti-alignment, excite inclinations, or maintain detached populations only after millions of years of steady influence. Human observation cannot directly watch such deep time shaping unfold. Simulation becomes the practical way to bridge the gap between present measurements and long-term dynamics. It allows astronomers to ask whether the structure seen now could reasonably have grown from past conditions under a particular hidden influence. Modern Planet 9 simulations have grown more realistic over time. Earlier work often focused on idealized conditions or on a limited subset of bodies. More recent studies have tried to include all 4 giant planets as active perturbers: early giant planet migration, passing stars, and the Sun's birth environment in a stellar cluster. Some recent work has also tested whether Planet 9 can explain not only the most exotic detached objects, but also more conventional long-period Neptune-crossing trans-Neptunian populations. In at least one such study, the Planet 9 inclusive model matched the observed orbital architecture of that group much better than the version without Planet 9. After observational biases were considered, that does not close the case, but it shows how simulations can turn a broad idea into a more specific set of predictions. The outputs of these models are not only explanatory, they are predictive. A good simulation does more than recreate what is already known. It suggests what astronomers should find next if the model is correct. It may imply that certain orbital tilts should be more common, that certain detached populations should exist in particular ranges, or that the hidden planet itself is more likely to occupy some parts of its orbit than others in order to preserve the observed architecture. These predictions then guide future surveys. If new discoveries continue to align with them, confidence can grow. If they do not, the parameter space for Planet 9 must shrink or shift. Parameter space is the range of allowed values for a model's key properties. For Planet 9, this includes mass, semi-major axis, eccentricity, inclination, and orientation in space. Semi-major axis is the average size of an orbit, while eccentricity measures how stretched it is. Different simulations explore different combinations. Some recent modelling has examined a somewhat lower mass planet than earlier canonical estimates, with a mass around 7.5 Earth masses, a moderately inclined orbit, and a semi-major axis around 600 astronomical units. Other variants remain under discussion. The important point is that the simulations do not all point to a single exact planet. They point to families of distant planets whose long-term gravitational effects may fit the observed outer architecture better than the no-planet alternative. Still, simulations cannot rescue a bad hypothesis merely by being elaborate. Their results depend on assumptions. The starting distribution of small bodies matters. The way discovery bias is modelled matters. The adopted history of giant planet migration matters. Even numerical details can matter when very long integrations are involved. This means that an impressive match between simulation and observation must always be read with discipline. The question is not whether one chosen model can produce the observed pattern. The deeper question is whether Planet 9 does so robustly across reasonable assumptions, and whether alternative explanations fail by comparison. That comparison remains central. Some astronomers argue that the apparent orbital clustering may weaken once survey biases are handled more completely. Others hold that the Planet 9 signal survives and even expands when broader trans-Neptunian populations are considered. The simulations therefore serve both sides of the discussion. They are used to strengthen the hidden planet case, and also to test whether the case rests too heavily on small number statistics or incomplete observational sampling. Observations indicate that Planet 9 remains theoretical. The existence of the far-off world still rests on gravitational patterns rather than direct imaging, and simulations are the main arena in which those patterns are judged for coherence. So this stage of the search is not about seeing the planet itself, it is about asking whether the outer solar system moves as though such a planet is there. Simulations take the faint orbital hints preserved in distant icy bodies and let them unfold through time under many possible hidden arrangements. Some runs produce outer systems that look strikingly like the one astronomers see. Others do not. From that difference comes a more disciplined picture of what kind of unseen world could still be responsible. The result is not final proof. It is a refined gravitational portrait, drawn not from light alone, but from the long patient motion of the outer dark. Even when a scientific idea is elegant and useful, astronomy does not accept it simply because it seems to fit. The Planet 9 hypothesis gains attention because it offers a coherent way to explain several unusual features in the far outer solar system. Yet coherence is not the same as proof. At this stage of the search, caution becomes part of the science itself. The question is no longer only whether a distant planet could explain the observed patterns. It is also whether those patterns might arise in other ways, or whether they may appear stronger than they truly are because the observations remain incomplete. This is the inner discipline of the problem, where alternative explanations must be held beside the hidden planet idea without preference for drama. The first alternative is observational bias. This is often the most important rival explanation because the distant objects that shape the Planet 9 argument are very hard to find. They are faint, slow, and detectable only during limited parts of their long orbits. Telescopes do not search all directions equally. Surveys differ in depth, sky coverage, season, and method. Some parts of the sky are crowded with stars, some are observed repeatedly, while others receive less attention. Because of this, the small known sample of extreme trans-Neptunian objects may not represent the full distant population fairly. A pattern that looks unusual in the discovered objects might look less unusual if the unseen majority were known. In that sense, the outer solar system may be offering not a false pattern, but an incomplete one. This caution becomes stronger because the sample size remains small. A few objects with related orbital directions can seem persuasive, especially when their geometry is drawn clearly on a plot. But small number statistics are fragile. Add several new discoveries and the pattern may sharpen, or it may soften. Remove one uncertain member and the significance may shift again. In fields where data are sparse, human judgment must resist the temptation to treat a suggestive arrangement as settled fact. Astronomy often works under such conditions, and it does so responsibly by acknowledging that the current sample may still be too limited for a final conclusion. A second alternative lies in the early history of the solar system itself. The giant planets likely migrate from their original birthplaces, and that migration reshapes the outer debris field. Bodies are scattered outward, trapped in resonances, detached from Neptune, or slowly altered through long-term gravitational effects. If the early solar system contains more mass in its outer disk than it does now, then collective gravitational interactions among many bodies may have played a larger role than the present-day architecture suggests. In this view, some of the strange distant orbits may be relics of a more crowded and restless past, rather than evidence of a single unseen planet still acting today. Passing stars provide another possibility, though one that is difficult to measure with confidence. The Sun likely forms in a stellar nursery, a birth cluster where neighbouring stars are more common than they are in its present galactic environment. In such a setting, a close early stellar passage could perturb the distant outskirts of the young solar system, lifting or stretching the orbits of outer bodies, even long after that birth environment disperses. The altered objects would remain as a fossil record of the event. A later stellar encounter, though less likely, could also affect the most remote populations. Such passages do not need to create the exact same pattern as Planet 9 to matter. They only need to show that distant detached or tilted orbits can emerge through channels other than a hidden planet. There are also proposals involving self-gravity and a once more massive outer disk, if enough material existed beyond Neptune in the past. The combined gravity of that extended population might influence orbital clustering or detachment without requiring a single dominant planet. This idea is harder to maintain under some models because the outer disk would need to possess particular mass and longevity, and much of that material is no longer present today. Still, it serves as a reminder that the current thin debris field may not be a faithful picture of the conditions that first shape the orbits now under discussion. The outer solar system may be quieter now than it once was. Another caution concerns the interpretation of simulations themselves. A model can appear successful if it is tuned to reproduce known features, but success under selected assumptions does not guarantee uniqueness. More than one mechanism may generate similar results. A hidden planet may cluster orbits. Certain histories of migration may also do so. Discovery bias may enhance the visual strength of either pattern. When several explanations overlap, science advances not by choosing the most dramatic story, but by testing which explanation remains robust across the widest range of evidence. That process often takes longer than public interest would prefer. Direct non-detection also plays a subtle role in this caution. If Planet 9 were brighter, warmer, nearer, or located in a well-searched part of the sky, it might already have been found. The fact that it has not been securely detected does not eliminate it, but it places pressure on some versions of the hypothesis. Each unsuccessful search removes easier cases from consideration. Over time, this pushes the hidden planet toward narrower combinations of mass, brightness, and location. A theory that survives such narrowing may become stronger, but one that survives only by retreating into more difficult and less testable corners must be handled carefully. Persistence alone is not proof. Even the term Planet 9 can create a false sense of solidity. The name sounds like a known object waiting only for a photograph. In reality, the scientific situation remains more provisional. The object is not a confirmed member of the solar system. It is a proposed explanation for orbital behavior in distant small bodies. That difference matters. A hypothesis can be useful, predictive, and mathematically well-formed while still being wrong. Astronomy has many such episodes in its history, where a discrepancy first suggests a new body, force, or mechanism, and later evidence either confirms or replaces the original idea. The discipline lies in keeping the proposal alive without letting the name outrun the evidence. So this region of the mystery is defined by restraint. Observations indicate that some distant orbits are unusual enough to require explanation. Models indicate that a distant planet can reproduce several of those features under plausible conditions. It remains uncertain whether that is the true cause. Bias, early migration, past stellar influence, and other dynamical histories remain active alternatives. None has yet closed the matter completely. None has fully dissolved it either. In this careful middle ground, astronomy does some of its most honest work. It neither dismisses the hidden planet idea because proof is incomplete, nor accepts it because the pattern is appealing. It keeps multiple explanations in view and asks which one continues to fit as new objects are found. New surveys deepen and new simulations are tested. The caution is not a weakness in the search. It is the structure that keeps the search trustworthy in the far outer dark. Uncertainty is not an empty gap. It is part of the evidence itself, held steadily until the sky yields more. If a distant planet is shaping the outer solar system, then its physical nature must be consistent with both the gravitational patterns observed and the limits placed by direct searches. This brings the focus inward from the field of debris and motion to the planet itself, not as an image, but as a constrained possibility. The proposed world is often described as a super-Earth or a small ice giant, meaning a body larger than Earth but smaller than Neptune, composed of rock, ice, and possibly a substantial envelope of gas. These terms do not define a single known object. They describe a class of planets whose properties can be estimated from mass, distance, and formation theory, even when the planet itself remains unseen. The mass of this hypothetical planet is usually placed at several times that of Earth. This range matters because it determines how strongly the planet can influence distant orbits over long times. A mass too low would not sustain the observed clustering in many models. A mass too high would risk producing effects that are not observed, such as stronger disturbances in the orbits of known planets or excessive brightness that surveys should already have detected. Within this middle range, a planet can act as a long-term gravitational organizer without becoming obvious in direct observation. Its presence would be felt more through motion than through light. Composition follows from mass and formation environment. In the outer solar system, where temperatures are low, volatile substances such as water, methane, and ammonia can condense into solid or liquid forms. A planet forming in this region or migrating into it may accumulate a mixture of rocky material and ices. If it grows large enough, it can also gather a gaseous envelope, dominated by hydrogen and helium. This combination is similar in broad term to Uranus and Neptune, though the exact balance of rock, ice, and gas could differ. The term ice giant reflects the dominance of these frozen volatile compounds in the planet's makeup, even though much of the interior may not be solid in a simple sense. Temperature remains a defining feature. At distances of hundreds of astronomical units, sunlight provides only a weak contribution to the planet's energy. The surface or upper atmosphere would be extremely cold by terrestrial standards. However, internal heat may still play a role. Planets can retain energy from their formation and release it slowly over billions of years. In a sufficiently massive body, this internal heat can maintain a temperature higher than that expected from sunlight alone. This does not produce visible brightness, but it may support a faint thermal glow detectable in infrared wavelengths under favorable conditions. The balance between external cold and internal warmth shapes both the planet's structure and its observational signature. An atmosphere, if present, would influence many of these properties. A thick gaseous envelope can trap heat, redistribute energy, and affect how radiation escapes into space. It can also determine how reflective the planet appears in visible light. Clouds of methane or other compounds could increase reflectivity, while darker layers or complex chemistry could reduce it. The atmosphere would not necessarily be uniform. Temperature gradients, pressure changes, and chemical reactions could create layered structures. Yet at such low temperatures and with such weak solar input, atmospheric dynamics would be slow compared with those on closer planets. The overall impression would be one of quiet, gradual change rather than rapid weather. The planet's orbit itself would contribute to its physical state. A highly elongated path means that the distance from the Sun varies significantly over the course of a long orbital period. At the nearer part of the orbit, the planet would receive more sunlight, though still very little compared with Earth. At the farthest part, it would move through even deeper cold. Over many thousands of years, this could create slow seasonal cycles on a scale far beyond human timescales. The atmosphere might expand or contract slightly. Surface or cloud chemistry might shift. These changes would be subtle and extended, not dramatic, but they would reflect the long rhythm of a distant orbit. Rotation also plays a role, though it is harder to constrain without observation. A planet of this type might rotate in a matter of hours or days, as many known planets do, or it might have a slower spin depending on its formation history and any past interactions. Rotation affects atmospheric circulation, magnetic field generation, and internal structure. A rotating fluid interior can generate a magnetic field, which in turn interacts with charged particles in space. Such details remain speculative for Planet 9, but they follow from general planetary physics rather than from specific observation. Density provides another indirect clue. A planet composed largely of rock would be denser than one dominated by ices and gas. If the mass and radius could be measured, density would reveal the internal composition. Without direct measurement, astronomers rely on formation models to estimate likely ranges. A super-Earth at large distance might be more compact and rocky. A small ice giant might be less dense, with a significant gaseous envelope. Each possibility leads to different expectations for thermal emission, reflectivity, and long-term evolution. The uncertainty in composition therefore feeds back into the uncertainty of detectability. The planet's origin is also considered. It may have formed closer to the Sun and been scattered outward during the early rearrangement of the giant planets. In that case, it would have carried its mass and composition from a denser part of the solar system into the outer frontier. Alternatively, it might have formed in place at great distance, though this scenario can be more difficult because material is sparse in the outer regions. A third possibility is capture, where the Sun acquires a planet from another star during a close encounter in its birth cluster. Each origin leaves different traces in orbital shape and inclination, but without direct observation, none can be confirmed. Despite all these considerations, the picture remains constrained rather than complete. Observations indicate that if Planet 9 exists, it must be consistent with the gravitational patterns of distant objects and with the absence of a clear detection in past surveys. It remains uncertain exactly what combination of mass, composition, atmosphere, and temperature it possesses. The planet is therefore best described as a range of physically plausible worlds rather than a single defined body. Each version shares the same broad character: cold, distant, moderately massive, and faint. In this inner layer of the search, the hidden planet becomes more tangible in theory while remaining invisible in practice. Its possible structure can be outlined. Its likely behavior can be described. Its thermal and reflective properties can be estimated. Yet none of these features has been directly measured. The planet exists here as a physical hypothesis shaped by known laws and constrained by observation. It is a world that can be imagined with discipline, but not yet seen, defined more by what it must be than by what it has been observed to show. If Planet 9 exists, its greatest importance may lie not in what it is, but in what it does. A distant planet far beyond Neptune would not dominate the familiar inner solar system in any visible daily sense. It would not brighten the night sky. It would not alter the seasons of Earth or the paths of the known planets in ways obvious to ordinary observation. Its influence would be quieter than that. It would work at the edge of the Sun's domain, where distances are enormous, motions are slow, and small repeated gravitational effects can accumulate across immense spans of time. In that far region, A hidden planet could help shape the architecture of the solar system without ever entering the awareness of the inner worlds. The first and most direct influence would fall on the distant trans-Neptunian objects, especially those on detached and elongated orbits. These are the bodies whose motions first suggest that some organizing force may be acting beyond Neptune. A moderately massive distant planet could steadily guide the orientation of their orbits, preserve patterns in how their long axes point, and maintain populations whose paths remain beyond Neptune's strongest present influence. This shaping would not occur through constant close encounters. It would emerge gradually, through the long, steady pull of gravity acting over millions of years. The result would be a kind of hidden ordering, where the small icy bodies preserve a record of a planet that may still evade direct detection. Tilt is another part of this influence. Most of the major planets orbit the Sun in roughly the same broad plane, though not perfectly. In the far outer system, some small bodies follow much steeper inclinations. A distant inclined planet could slowly excite such tilts, drawing some objects into paths that rise far above or fall far below the common plane of the solar system. Over long times, this could create a more vertically structured outer population rather than a simple flat extension of the planetary disk. The outer system would become not only stretched in distance, but twisted in angle, with the hidden planet acting as a quiet source of orbital variety. This influence can extend to long-period comets as well. Comets from the deep outer solar system spend most of their existence in darkness and cold, returning inward only rarely. Their paths can be altered by many effects, including the gravity of the giant planets, passing stars, and the weak tidal field of the Milky Way. A distant planet would add another source of slow perturbation. It would not necessarily send comets inward in dramatic bursts, but it could help redirect some outer bodies onto new orbital paths over immense spans of time. In this way, the hidden planet would become one of several quiet sculptors of the long comet reservoir, changing which icy bodies remain distant and which eventually drift toward the inner solar system. The detached objects are especially important here because they seem to live in a middle state. They are too far from Neptune at closest approach to be explained easily by its present-day influence alone, yet they remain within the broad-bound system of the Sun. A hidden planet offers one way to maintain such bodies in this detached condition. Its gravity could lift their nearest approach distances, preserve their separation from Neptune, and help keep them on long stable paths that rarely enter the more crowded regions of the known planets. If so, the distant planet would not merely coexist with these bodies, it would help define the population itself. There may also be effects on the long-term stability of the outer solar system. Stability in celestial mechanics does not mean stillness. It means that orbits remain bound and structured without dissolving into rapid disorder. A hidden massive body changes that structure. It creates new resonances, new zones of long-term stability, and new corridors of slow orbital diffusion. Some objects may remain trapped in protective rhythms with the distant planet, just as Pluto remains in a resonance with Neptune. Others may be gradually destabilized and shifted onto more unusual paths. The outer solar system would then become a more intricate gravitational web than the known planets alone would produce. This broader architecture matters because the solar system is not only a collection of isolated worlds, it is a connected dynamical system in which mass placed far away can still influence structure through time. Planet 9, if real, would enlarge the solar system in a meaningful physical sense. It would extend the region in which major planetary gravity actively shapes the orbital map. The known giant planets would no longer define the last strong planetary layer. Beyond them, another gravitational province would exist, one colder and slower, but still distinctly planetary in its organizing role. There is also a deeper historical significance. The present arrangement of distant bodies is a memory of the solar system's past. If a hidden planet helps maintain that arrangement today, then it also becomes part of the history that produced the current architecture. Its orbit may preserve traces of early migration, scattering, or capture. The outer debris field may in turn preserve traces of its long rule. In that sense, the planet would not be an isolated addition to the solar system, but one participant in the long shaping of the whole system. It would help explain not only where some distant objects are now, but why the outer solar system develops the structure it has instead of some other structure. Yet the influence must be described carefully. Observations indicate that the known planets already explain much of the solar system's architecture very well. Planet 9 is invoked mainly to account for specific outer patterns that seem harder to reproduce otherwise. It remains uncertain whether those patterns truly require a hidden planet. If future surveys weaken the clustering signal or show that observational bias has overstated the apparent order, then the proposed influence of Planet 9 would shrink accordingly. The planet's dynamical importance therefore depends on the reality of the evidence that first suggests it. If the evidence does hold, then the hidden planet becomes something quietly profound. It would mean that the solar system is still not fully mapped at the planetary level. It would mean that the distant architecture of icy bodies, detached orbits, and rare comets is being shaped by a world only indirectly known. It would mean that the edge of the planetary system is not Neptune alone, but a broader and more complex outer arrangement in which another planet moves slowly through deep, cold, and weak sunlight. In this inner stage of the mystery, the hidden world is felt most clearly through the motions it may have impressed on everything around it. The small bodies become the visible script of an invisible author. Their long years, tilted planes, and detached paths carry the possible signature of a planet that acts from far away without ever approaching the familiar worlds. Whether that signature proves real remains unresolved. But if it is real, then Planet 9 is not simply another remote object. It is a quiet architect of the outer solar system, shaping the distant boundary of the Sun's family through gravity alone. At the innermost layer of this mystery, the search for Planet 9 becomes a meeting point between what gravity suggests, what telescopes can exclude, and what remains hidden between those two. By now, the broad outer darkness has narrowed into a more disciplined problem. The question is no longer whether the far solar system is large enough to conceal another world. It clearly is. The question is not even whether a distant planet could in principle shape remote icy bodies. It could. The question is whether the evidence now available forms a coherent enough picture that the hidden orbit can be outlined with real confidence. This is the closest point in the search, not in physical distance, but in explanatory reach. Here the unseen planet is approached through the smallest surviving uncertainty. The first part of that inner picture is gravitational. The unusual orbits of some extreme trans-Neptunian objects remain the strongest reason that Planet 9 is still taken seriously. These bodies do not simply occupy the outer solar system. They preserve orbital features that appear more ordered than chance may easily allow. Their long axes, detached nearest approaches, and in some cases their steep inclinations all suggest that the outer region may be shaped by a continuing influence rather than by past scattering alone. Yet this evidence remains indirect. It depends on a limited sample, and its strength changes as surveys improve and new objects are added. Even at this closest stage, the gravitational case is suggestive rather than final. The second part is observational. Telescopes have now searched enough of the sky, in visible and infrared light, to rule out some simpler versions of the hidden planet. A nearby bright giant world is no longer a comfortable possibility. A very warm or easily seen distant planet in some well-covered regions would likely have been found already. This matters because it compresses the hypothesis. The planet, if real, must inhabit a narrower range of brightness, distance, and sky position than a loosely imagined unseen world once could. It must be dim enough, slow enough, or placed in difficult enough fields to remain beyond secure detection so far. Observation has not dissolved the mystery, but it has made it more exact. These two lines of evidence do not yet join perfectly. Gravity points toward the possible need for a hidden world. Direct observation has not yet supplied that world. In some scientific problems, this gap closes quickly. In the outer solar system, it closes slowly. Because the scale is so large and the signal so faint, a planet hundreds of astronomical units away may spend most of its long orbit in regions where it is extremely difficult to detect. It may move so slowly that repeated observations must be spaced with care. It may lie against dense stellar backgrounds or beyond the practical limits of past wide surveys. The absence of direct detection therefore carries meaning, but not a final verdict. At this depth of the search, astronomers work by tightening the remaining possibilities. A hidden planet of several Earth masses on a distant elongated orbit remains one of the most discussed versions because it best balances the gravitational requirements with the limits of non-detection. Its orbit is usually imagined as both large and tilted, with a period so long that one full circuit around the Sun would take many thousands of years. This means the planet would spend most of its time far from the part of its path where it might be easiest to see. The search is therefore biased not only by where telescopes look, but by where the planet itself would linger for the longest time in its own slow motion through the dark. Even the phrase where it is hiding must be handled carefully. The current state of knowledge does not identify one secure location. It identifies allowed zones and disallowed zones, preferred geometries and weakened ones. The hidden orbit is not a thin line drawn with precision across a star chart. It is a family of plausible paths that survive both dynamical modelling and observational limits. Some parts of those paths are harder to search because they lie in crowded fields. Some are harder because a cold, distant planet there would be fainter than earlier assumptions allow. Some remain open because no single instrument combines enough sky coverage and enough depth to close them all at once. James Webb belongs to this innermost stage as a tool of refinement. Its infrared sensitivity allows astronomers to inspect selected candidate regions with unusual depth, asking whether a faint cold source might be present where other data now point. Yet even Webb does not erase the central difficulty. It does not survey the whole sky broadly enough to perform the entire search alone, and a candidate source still requires repeated observation to prove slow motion. What Webb offers is a way to reduce the remaining darkness more sharply. It can test whether a possible hiding place contains a thermal signal that fits a distant planet better than the background does. In doing so, it helps transform wide suspicion into narrower scrutiny. This is also the point where scientific language must remain the most disciplined. Observations indicate that the outer solar system contains patterns worth explaining. Models indicate that a distant planet can explain several of them coherently. Direct searches indicate that some versions of such a planet are already disfavored. It remains uncertain whether the surviving region of possibility contains a real world or only the last shape of an attractive hypothesis. That uncertainty is not a weakness of the evidence. It is the exact boundary of what the evidence presently supports. If Planet 9 is eventually found, this innermost region of the mystery will be remembered as the stage in which the planet existed most clearly in absence, its mass, orbit, and nature will have been approached through orbital disturbances, missing detections, and the logic of elimination before any confirmed image secures it. If it is not found, then this same stage will remain important for a different reason. It will show how far a coherent gravitational pattern can lead thought before fuller observation demands another explanation. In either outcome, the search has already revealed something significant about the solar system. Its outer architecture is richer, subtler, and less completely known than once assumed. So the journey inward ends not at a visible planet, but at the tightest current boundary between inference and sight. The broad frontier has narrowed to a small surviving uncertainty shaped by distant orbits, faint thermal expectations, incomplete sky coverage, and the patience of repeated search. The hidden orbit is now less a fantasy of emptiness than a constrained possibility suspended inside real evidence. Whether that possibility soon resolves into a world or slowly fades under better data remains unknown. For the moment, the far outer solar system still holds one final quiet space where gravity seems to point. Light has not yet confirmed, and the search rests closest to its unseen goal. The search now grows quiet again, far beyond Neptune, beyond the bright authority of the known planets. The outer solar system remains wide, cold, and only partly red. Its small icy bodies continue along their long paths. Their faint motions still carry traces of the forces that shape them. Some of those traces appear orderly enough to suggest a distant planet. Some remain uncertain enough to resist any final claim. The balance between those two conditions is where the mystery rests. James Webb does not end that mystery, but it deepens the way it can be examined. Its infrared vision reaches into weak thermal light, where a cold, remote world may leave a faint signal of its presence. Other surveys continue to widen the map, exclude easier possibilities, and refine the sky regions still worth attention. Simulations continue to test whether the distant architecture of the solar system moves more naturally with an unseen planet than without one. Each method contributes a different form of patience. None speaks alone. For now, Planet 9 remains a careful possibility rather than a confirmed world. Observations indicate that the outer solar system preserves unusual patterns. It remains uncertain whether those patterns are the work of a hidden planet, the result of incomplete discovery, or the memory of older events written into distant orbits. This uncertainty does not empty the search of meaning. It gives the search its shape. It keeps the question precise, steady, and open. In the far dark, the sun's family has not finished revealing its full extent. The known planets end, but the gravitational story continues into weak light, cold dust, and slow invisible years. There, among the most distant paths bound to the sun, astronomy keeps looking with restraint and care, waiting for motion, heat, and geometry to settle into a clearer answer.